If given a chance, we'll probably do a problem from the sheet again, or we'll do a fresh question towards the end of today's class. What I intend to do today is to continue with the where we left off the other day. There were a few things which we in fact covered up on that class. We covered a few relationships, okay, and like I said, those relationships, it's worthwhile, remember them because they're quite handy tools when you need to do some back of the envelope calculations. So the first one was gamma dry was given as gamma bulk divided by 1 plus water content. There was also an expression for porosity N equal to void ratio divided by 1 plus void ratio. We also looked at some relationships which were quite handy to use, which was SC equals to WGS, where S is the degree of saturation equals to volume of water over volume of voids. Okay, specific gravity GS was gamma solids by gamma water, and we did say specific gravity, the usual value of specific gravity varies by around 2.6, so it fluctuates around 2.65 or so. We looked at other relationships, and one of the important one was gamma bulk was equivalent to GS plus SC over 1 plus E whole thing times gamma water. Okay, that was another expression which, because of which we could because of this expression we could derive other expressions for gamma gamma dry, gamma saturated, and gamma submerged or gamma buoyant was gamma saturated minus gamma water. Okay. Today we intend to continue, and we'll start off with index properties. So, like I said, index properties in fact leads to classification of soil. Classification of soil is yet another important subsection which we will not be able to cover up in these first 15 lectures, but I suggest after today's class the instructor in charge in your classroom, I request him or her to cover this section on classification. Soil classification is something which we would not be able to cover in these video lectures. I repeat, because we intend to add shear strength and some other sections towards the end of this 15 lectures or so. So let's start with index properties. Now index properties to begin with, we say the soil which occurs in a variety of shape and size. Okay. I believe this particular the file has already been downloaded, so I'm just continuing from where we left the other day. We say the soils, they occur in large variety of shape and size. You pick up a handful of soil, anything you can see with the hand lens is we call this as a as a thumb rule, you can call it as a coarse grain deposit. Anything you can see with either naked eye or using hand lens. So whenever we see group of soils, we like to place the soils which have similar properties. When we say properties, we are mainly concerned with the mechanical behavior. The three important properties would be the shear strength, permeability, and compressibility. So these are the three, as an engineer, if you are aware of these three properties of the soil, I would say as an engineer, our job is well done. So we like to place them in groups which have similar properties, and these groups are quite often called as classification systems. And like I said, classification, there is no unique classification on this in this world. For example, the American themselves, they follow three different classification systems. The most popular one can be the ASTM or the ASHO. So usually we follow either the USCS classification or the ASHO, and the third commonly which we adopt is the IS classification. So many a times, when we do any division of soil, we either follow IS classification or the ASHO. The USCS classification is very similar to IS, and I repeat, I request the instructor at your various colleges, I request him or her to do this at your end. So let's look at some the very first one. How do you index the soil? The first thank you. So the first one is is based on particle shape. So like I said, if you can examine the particle with your eye or even with a hand lens, we say that we crudely can say that it is a coarse grained deposit. Okay, so over here we have a representation of 4 different shapes, and these shapes are more important for coarse grain. So the very first one is, if you scroll from left to right and then bottom, you will see the shape becomes more sharp, more angular, more pointy. So the rounded shape is a very smooth. There definitely you can't see any edges. You can rub your finger all around, and it's smooth piece of gravel. Most likely you will find this along the river beds. If you go to say the next one, sub-rounded is as if the edges are still smooth. You rub your finger, you can still feel, you still can't feel the edges, but you can, from your eye, you can see that the edges have somewhat not been fully rubbed off. That would be sub-rounded. You go down, the sub-angular is, the edges, you can feel the edges. And the last one is angular, where the edges are quite pointed. Now these are pretty important for in order to understand some of the engineering properties. So let's take for example the shear strength. And if I'm looking at the last one, the angular shape, what we see is, if you pack the particles together, the particles are going to be kind of interlocked. So the interlocking in fact helps to increase the strength. Take an example of a stress strain curve. So can I have this? Can I just shut this because that's being a disturbance? So take an example of your a stress strain curve. So strain is usually written by epsilon, stress is sigma. Remember, when we speak about shear strength, we are probably going to look into this. So a stress strain curve for any soil typically can be a hump shape. So you have a transient peak followed by drop. Now the hump, the size of the hump is governed by the angularity of the particle. More angular the particle, somewhat they control the size of the hump. So denser the particle, of course the size of the hump is also governed, but what we see is the density is one factor, but the interlocking is also plays a bigger role, a greater role in the thank you. Interlocking also plays a greater role in the strength characteristics. Okay, I'm still getting used to this interface. Apologize. Now, since we are looking at the photographic view of the particle, it's really not a good idea to classify the soil based on just the shape, because what you would be looking at the shape and what I would be looking at the shape may not be the same. in a sense it's just a qualitative uh, view, a qualitative description. You can't give numbers. In fact, it's also subjective to, where different persons reading out different numbers. So more or less, we say that there is no universally accepted grain shape. Grain shape is difficult to, look at. What we normally follow in nomenclature is something for bulky grain. So the topmost one is the bulky grain. Bulky grain would be characteristics of sand and gravel. Again, meaning the particles you can see with your eye, naked eye, or with hand lens. River gravel, wherein the forces are aggressive, the natural forces are aggressive, they would make the particles more rounded, and where the the flow is gentle, so you have a sands leading to sub-rounded and to maybe to angular. So we have go down, we have flaky grains. Flaky grains, and the last one is needle-shaped grains. Both these are characteristics of fine grain deposit. A fine grain would include your clay as well as silt. So we are looking at clay and silt particles, which of course you will not be able to view from naked eye or with hand lens. These particles, the flaky particles, are very similar to your cornflakes which you have. It's like a flake wherein one dimension is lot less compared to the other two dimensions. So examples of flaky would be micaceous soil, the soils which have mica content, and the clay content. These clay contents, the crystals of micaceous or the clay crystals are flaky in nature. Okay, so flaky is one. The second one is needle shape. Needle shape are also characteristics of your fine grain. In particular, a particular clay looks like needle shape. So we got an example of one particular clay. This clay mineral is called as kaolinite. So kaolinite clay mineral is something which has needle shape particle. So like a needle, only the one dimension is much larger than the remaining or the other two dimensions. So it looks like needles stacked or collection of needles. We will look at kaolinite clay mineral when we do clay mineralogy in the next class. So we have, that leads to the shape, and like I said, shape is not a good idea to quantify the number. You're only looking at quality of the shape. The more quantification can be done by particle size distribution. Particle size distribution, we look at the distribution because the entire range of particle size, if you look at from the gravel size going down to clay content, the order of magnitude is 10 to the power 8. It's a huge number, meaning you look at one order is one cycle, so you're looking at 8 cycles of order. And we normally represent the particle diameter, soil particle diameter, knowing that the diameter is not, particles are not spherical in shape. So what we look at is, in fact, equivalent diameter. So we look at the equivalent opening size of a grid, and equivalent diameter of the soil particle is taken. So usually, like we said, it's the range is too large, 10 to the power 8 or so. So if you want to represent this on a scale, we take a logarithm scale. Now log scale or logarithm scale we speak about is a scale which is with respect to the base 10. I would like you to, after the class, go home and look at how a log scale is plotted. Meaning if you're given a sheet of paper and on the sheet you're asked to fit in a log cycle or maybe 3 log cycles, look at how each log cycle is plotted. It will help you to understand better how log scale looks like. So we usually represent this in a semi-log, meaning one axis is not a log, the other axis is a logarithm scale. So in this plot we look at both coarse grain and fine grain. So the entire range of soil particles are usually plotted in this distribution. the two methods of grain size analysis, like this will probably would be better covered if you do some simple experiments to determine the particle size distribution, that's PSD of coarse grain. It's usually done by sieve analysis. A stack of sieves very similar to what you put for your you sieve any particles, the same similar sieves you use for soils. The stack of sieves are taken, and the largest opening is kept at the top and the smallest opening is kept at the bottom of the stack, which helps us to determine the distribution of coarse grained soils. The distribution of fine grained soils is not that easy because they are mainly colloidal particles. They like to float around in water. So we use either the hydrometer analysis or the pipette method. Now the IS code also says there is a third method, an alternate method, which is Plumpett method, Plumpett balance method to be precise. However, all the results are calibrated or compared to the hydrometer. So it's the most commonly used method is the hydrometer. Again, I would like you to really go back and practice this if given a chance to do hydrometer test in the lab. Now, I'm not sure if you're able to see this very clearly. Then the size is too small. But let me zoom out first. Zoom out. This normal. Okay, thank you. So in a sense, without going into what these are, this is an example of a range of particle size for different codes or different methods which they follow. Now, in topmost is the ASTM. Like I said, the Americans are also are quite confused about which method to follow. The ASTM is one American method. The ASTRO is the second American method. And the USCS is the third American method. And like I said, if you go back home, ASTRO is a good classification system. I would like you to study this, as well as the USCS. USCS is very similar to our IS classification system. The last one is the British one. The British one is again, we are not looking at the classification, we are looking at the range of particle size which are defined by the various methods. Now, because this is not a good scale to show, I have another document which I will just upload, which is maybe is a better version to show. So I hope you are able to see this. In a sense, this is a photocopy of what our Indian standard distributes the soil particle into various size. Now. Thank you. Okay, what these numbers are, some of these numbers are pretty important and I would like you to remember as a tablet. Please take them as a tablet. These are important numbers and they should be at the tip of your fingers. For example, the division between the sand and gravel is 4.75 millimeter. Okay, that's 4.75 millimeter equivalent size. Or compare, this is IS classification. If you follow the British standard, this is somewhere at 2 millimeters. So we are not going to look at various size for what other codes follow. Let's simply look at IS code for the time being. 4.75 millimeter is a good number to remember, which is the division between gravel and sand. Likewise, 75 micron or 0.075 millimeter is a good number to remember, which is a division between fine grained soils and coarse grained soils. So anything on the left hand side is the coarse grained soil. That's 75 micron or 0.075 millimeters. There are other numbers to remember. Again, the border between medium and coarse grained is 2 millimeters. Usually, a 0.425 millimeter is an important number to remember. When we do some laboratory test, this is an important sieve size or particle size below which or finer than which we normally do a lot of tests for either index property determination. So 0.425 millimeter or I would say 425 micron is the border between fine grain, apologize, is the border between fine sand and medium sand. Likewise, the 80 millimeter is the border between gravel and cobbles. I hope some of these are fine. So with time, I'm pretty sure many of you would be able to pick them up. Let's go for our handout. Yep. So like I said, these numbers, if I can zoom in, okay, we said British standard 2 millimeter is the border between sand and gravel. Likewise, we are very happy with use of UCS. UCS system is very similar to our IS system. So the 4.75 millimeter is border. The only thing between UCS and our system is UCS stops at 75 micron for silt and clay, whereas our IS system also divides this thing further. So if we have silt is between 75 micron and it goes down to somewhere here which is 2 micron, and clay is anything less than 2 micron. It's in a sense it's just colloidal particle. It's hard to determine the particle size with certain degree of certainty. Okay, so let's move on to the next slide, please. So we said the range is quite large. So what we have done over here is zapped a figure which shows on the horizontal axis or the abscissa axis, you see the particle size or the diameter ranging from 1 micron, so that's 0.0001, okay, and it goes up to something like 100 millimeters. And on the vertical axis or the coordinate axis, what you see is percent finer, and you determine this by weight. So meaning if this number starts from 0, 20, 40, 60, 80, so somewhere 80, if I move across, anything less than this 80 means 80% is finer than the or the 80% of the particles are somewhere here below this curve. Alright. So this is a nice representation, and we usually use this log scale. So let's look at this. So from 100 to somewhere here 10 is 1 log cycle. So this being 10, the next line is 11. I apologize again, sorry. This is 10. So somewhere here is 20, 30, 40, 50, 60 and so on up to 100. What you see is the distance between 10 and 20 is large and the lines start to squeeze in. Similarly, this is 1 and that is 10. So 1, the next line would be 2, 3, 4 and it goes down to 10. And what you see is again the lines start to squeeze in. So that's 1 log cycle for us. And again, I would like you to go back, I repeat, and see how a log scale is plotted. You can easily buy this from the market, but it's a good idea to plot log scale. Use a normal spreadsheet, for example, your Excel sheet to plot a log scale. So we have various test results. These are the examples taken for a few particle size. And let's look at curve 1. Curve 1 is over here, shown by the broken line. If you follow this curve, what we see is it starts from gravel, going down to sand and silt. So it's like a curve which goes through the entire range. And usually, you know, this curve has some amount of convexity upward. So you can see there's a convex shape, upward convex shape. Okay, I hope you can recognize this. This first one curve is usually written as well graded. So the gradation is good in the sense it represents the more or less the entire range of particle size. Okay, I should mention that you have a log cycle of 100 over here and finer over there. I could have very well reversed it, meaning taken this 100 on the other side and this finer of 1 micron on the other side. It just is the same. Okay, 0.001. Okay, this is 1 micron. This is 1 micron. So this is where the clay particle should start from here. Sorry, from here. So anything less than 2 micron is clay. So that's clay for us. 001. So let's come back to the well graded. So that's well graded for us. Let's look at the second curve. Curve 2, which is here. That's curve 2 for us. What you see is there's a steep drop. So there's a steep drop, meaning there is majority of one particular particle size. So what we see over here is somewhere over here is less than this is fine, somewhere here is medium. So what we see is there is excess of medium sand in this particular plot. Okay, so this again is, like I said, looking at the curve, if I say that there is excess of particle size, again there is, unless we bring in numbers, we will bring in numbers in the next few slides. For the time being, this curve gives a feel that there is a sharp drop. So whenever you see a sharp drop, you should see that there is excess of one particular particle size. I can rephrase this statement, that there is deficiency of particle size of other particle size. So such a curve is uniformly graded. We call this uniform size or uniformly graded soil. Let's go to curve 3. Curve 3 is this curve. What you see is there's a flatness. In between there's a steep, and in between there's a flatness, and then followed by steepness. The flatness probably represents that there is no unavailability of this particular size, meaning from this size to this particular size there is unavailability of the soil, or there is deficiency of this soil. So when there is deficiency or unavailability, we call this gap. There is a gap. So we call this as gap graded soil. Now together, the gap graded and the uniformly graded together are called as poorly graded. It's important to remember both the soils are called as poorly graded. Compare this to the broken line, which is well graded. A well graded soil would have a better interlocking. So better interlocking would mean, again, the mechanical behavior or the shear strength is bound to be better. So there are set of terms or definitions which we use in order to look at whether it's well graded or if it is poorly graded. Okay, so I'm going to zoom in over here. So there is a term called coefficient of uniformity or Cu, and the coefficient of curvature or Cc. Cu is defined as the ratio of D60, where D60 is the grain size diameter which corresponds to 60% passing by weight. Okay, or in other words, 60% of the particles are finer than this particular diameter. Okay, so D60 is 1. So from the grain size plot, distribution plot, I would read out the particle size corresponding to D60. And similarly, I would read out particle size corresponding to D10, where again D10, if I look at the same definition, is grain diameter corresponding to 10% passing. So this ratio Cu, if Cu is we say we determine Cu value, we also determine Cc value. Cc again we read out a D30 and divide this D30 square by D10 times D60. We evaluate both the numbers. If in case Cc, which is the second one, D30 square by D10 times D60 is between 1 and 3, and if Cu, which is again D60 by D10, Cu if it is more than 4, we say that it is well graded gravel. And if Cu is more than 6, we say it's well graded sand. Remember, we have to look at the curve to evaluate whether it is sand or gravel. This will come in classification system, but however, if you're looking at sand, and if in sand if Cu comes to be more than 6, you say it is well graded sand. Likewise for gravel, you look at the number. So I'll leave a grain size distribution over there, which probably should lead to the classification system. So that is left to your center. We'll move on to look at what is clay consistency. Consistency is always only associated with fine grain deposits. In other words, fine grain deposits which have plasticity, which have sticky nature, and which have clay content. So the very first one, if you look at this table very carefully, it shows what the right hand side of the table shows shear strength. Now we're going to look at undrained shear strength much later if given a chance, but shear strength is the strength of the soil. Okay, and left hand side is the consistency, meaning how you define or identify the range of shear strength. So Atterberg, in fact, when Atterberg came out with this idea of laying down the strength of soil in terms of consistency, probably this table was a development of his as a result of his work. This table came out as a development. Let's look at the undrained shear strength of 20. In fact, to give you an idea of anything less than 20 is something like a butter. So similar to butter, the strength is too low. Okay, it's quite difficult for a person to walk over this without not sinking his or her feet into the ground. So for such deposits, we call this that they are very soft. The consistency is very soft. If you go down the table, from very soft it comes to stiff to hard. Hard would have a strength of more than 300 kilonewton per meter square. So kilonewton per meter square is similar to kilopascal. So anything strength more than 300 kilopascal is hard, meaning even if I take a sledgehammer, I find it very hard to break through. So that's 300 kPa or kilonewton per meter square. So looking at this table, okay, Atterberg, came out with this range of limits, or we call this as Atterberg limits. This came out as a result of Atterberg's limit work related to agriculture engineering. So let's look at the Atterberg limit for what in fact he looked at. He looked at a range. So if I look at from left to right, the water content in fact starts to reduce as we move from left to right. So let's look at the left hand side first, okay, where the water content is high. Remember, this water content high meaning the soil behaves like slurry. It's easy to flow, it just flows. If I throw a bucket of slurry on the ground, the soil will flow. Okay, that's high water content for us. If the water content gradually starts to reduce from left to right, what you see is the uh, consistency of the soil starts, it moves from, it now turns to soft, okay, meaning it starts to behave like ductile, it's easy to mold, okay, it's easy to mold, so it's some amount of ductility starts to come in. At this limit, which the water content starts to reduce, wherein the soil is soft, we call this as the liquid limit. The liquid limit is the water content. It's a water content wherein some amount of ductility starts to increase. Below this line, it's easy to remold the soil. So starting from here, you can easily remold the soil. To give you an idea of this range, the strength of the soil on this boundary, let's look at the strength. Remember we said, we spoke about strength on the previous slide. The strength on this slide, on this line is around 1 to 2 kilopascal. It's nearly 0, 1 to 2 kilopascal. We can't, it's impossible to measure using conventional laboratory equipment. If you go down, wherein some ductility starts to develop and it's easy to remold the soil, at a certain range, it will be hard to remold. Hard to remold without breaking it. So in the sense, your soil becomes brittle. Okay, this limit, Atterbuck called it as plastic limit. Okay, where it's you remold it and it starts to break off. So it becomes brittle. Somewhere between the plastic limit, which again is a water content, if you go down and decrease the water content, there is a term called shrinkage limit. Meaning, as we were moving from left to right, the soil actually had started to shrink or reduce its volume. It reduced its volume to this value. Below this value, the soil will no longer shrink. That's the volume it has reached. There won't be any change in volume below this. In fact, this shrinkage limit is important for us because somewhere below the shrinkage limit, let me draw an imaginary line over here. So somewhere over here, your degree of saturation is still 1. So remember, starting from here, if you go down to this value, the degree of saturation is still 1. Sorry, you can write. Okay, it's still 1. So, however, shrinkage limit, we normally determine the liquid limit in laboratory. We determine the plastic limit in laboratory. Remember, all these are water content, but we do not usually determine the shrinkage limit. Shrinkage limit is something which not much, not many people would like to work on. Can you guess? Those of you who are familiar with doing some laboratory tests, maybe you can guess. Shrinkage limit is not very popular because you need mercury to do this test, and mercury is a poisonous material. Meaning you handle mercury, if mercury gets stuck within your fingernail, your lifespan reduces. I mean, there are a lot of dangers associated with mercury. So shrinkage limit is usually not recommended in many laboratories. Liquid limit and plastic limit, let me just quickly go through how a liquid limit will be determined. Both liquid limit and plastic limit, in fact, if you look at the 425 micron number, which we said is an important number to remember, or 0.425 millimeter is the border between medium sand and fine sand. So we are looking at particle size which includes fine sand, silt and clay to determine the liquid limit. Now, many of you would ask, liquid limit is normally associated with clay. Maybe plastic silts to some extent. Why would you do the test using fine sand? That's a good question. If you have thought about it, I would like you to really examine this. Why would you use 425 micron sieve to do the liquid limit? Now, your guess is as good as mine. There is no, I would say there is no justification for this. The only thing is, let's blame it to Etterberg. Etterberg probably, at that time did this test using 425 micron, and he laid standards. So even today, when we do these tests, we have just followed the guidelines or standards such that, when I do a test somewhere in my part of the world and you do your test in your part of the world, we can compare the results. The standards are just based on these numbers generated by Etterberg. The first one, in order to do the liquid limit thing, the first method is by Casagrande. The Casagrande method is very popular. Our Indian standard recommends this method. It's a what we do is we make a groove in the soil, in a part of soil we make a groove, and this groove I repeat, we take a part of soil and we make a groove. This groove is made using some standard tools, and what we do is we blow this part up and down, and when blow this up and down till the point that the two halves of the groove meet. So number of blows required for the two halves of the groove to meet is counted. And if this number is 25, we call this the water content of this part of soil, we call this water content as the liquid limit. So I'll come back to this slide. Let me go to the next slide and show you the figure. So that's an one original Casagrande apparatus, okay, with this Casagrande tool. So this Casagrande tool is to make a groove. So I'm not sure if you can look at this. The picture is quite dirty, but there is a groove. There's a part of soil, and in between the part there is a groove. So this groove has been made by this elongated edge of Casagrande tool. Remember, this Casagrande tool is like a fan-shaped tool. Now the Americans, they were not happy with the usage of Casagrande for long, so they have modified this Casagrande tool to ASTM tool. So you would normally see a hook shape. ASTM tool is like a hook. So that has its own usage, and they like to use that hook. There are school of arguments over this. People who are against the hook, they will say, the hook is not able to control the height of the pad. Remember, this test is, in fact, if you look at this carefully, you make failure of the slope. The slope gets failed. The two ends or the two sides of the small miniature slope fail. So it's like a slope failure. Okay. So the groove, one set of people, they say that the height of the slope is controlled by this tool. Okay. If you look at the shape carefully, the height is controlled because it's like a fan. So if you rub this fan, it will control the height. The ASTM people, they say no. We will use the ASTM tool because it is easy to groove through, even through soils which have low plasticity. So depending on which school you follow, you're free to choose your own tool. However, the Indian standard, because we like to please both the people, so we say you can use either of the two tools depending upon how much of plasticity or how much of stickiness is there in your soil. So please refer to the IS code for the relevant tool. So let me come back. So what we do is we give blows, meaning make this go up and down, and count the number of blows required to fill this gap. If I go back, previous slide, okay. So we count the number of blows, and when the number of blows are 25, we say it's liquid limit or LL. Now there's been a lot of work done on this particular method, and a lot of people now agree that this method is subjective, meaning if I give this test to allow you to do the test, and you count the number of blows and you do the test, your count or your test when may not be the same as what I would be doing it. That's what it depends on the operator. And if your experience is much better than the third person's experience, your results are bound to be different. So we call this as subjective. So people argue that you don't need someone to dedicate his or her life just on Casagrande method to just to produce more authentic liquid limit result. So people, this group of argument, they move on to the next method, which is the fall cone method, in which you in a cup of soil you make a cone fall. This cone is 80 gram weight and it has a tip angle of 30 degree, and you measure how much of this is penetrated. If it penetrates by 20 millimeter, you say this is liquid limit. So in this case, you only measure the amount of penetration. So the subjectiveness which was there is not there in this fall cone. Incidentally, the British code recommends that you use this method. It says don't use Casagrande. Casagrande is out. Unfortunately, our IS code recommends the Casagrande. It's just the opposite, and it says for fall cone you can use as an alternate method. I'll leave this to you, wherein you would like to live in peace. The second one is the plastic limit, wherein you roll. You roll a thread into small diameter and you roll until it reaches 3 millimeter. If at 3 millimeter, if it begins to crack, you just collect those particles. And if it does not begin to crack, you remold the soil again into a ball and start rolling again. So this process is repeated, rolling up to 3 millimeter, and you see whether it's cracked up. If not cracked up, you repeat the process. And you collect those threads which have cracked up, and you measure the water content of these threads. The water content will give you the plastic limit. So this again, plastic limit is again based on experience of the operator. If your operator is not so experienced, it's you can get a very strange number. There are people who are working on alternate methods to determine plastic limit, and it's just an ongoing research in many universities. And some of the methods have been, alternate methods have also been developed. So there is a term called plasticity index, which is the difference between the liquid limit and the plastic limit. And I would like you to remember this plasticity index. It's a term which is important to to remember. Now, before I move on to the next slide, there is some term which is pretty important. And again, I would like you to remember this term and take it as a tablet. It's called as liquidity index. Liquidity index, or sometimes some people like to call it as normalized water content. Meaning it's water content minus plastic limit divided by the plasticity index. So in other words, if liquidity index is 1, it means my water content is the same as liquid limit. So at liquid limit, my liquidity index would be 1. What about plastic limit? So plastic limit minus plastic limit, 0. So at plastic limit, my liquidity index is 0. It's a good number to remember because it gives a feel of the strength of the soil. In order to understand this, let's look at the figure on the right. Please ignore the numbers, they are hardly visible. These numbers do not matter or irrelevant for us. But what we mean is, on the vertical axis or the coordinate axis, you see the liquidity index, that's over here. And on the horizontal axis, it's the strength of the soil. And there are various clay which have been taken, okay, clay various regions. What we see is, the range. So somewhere over here is liquidity index of 1. So you're at liquid limit. If you move horizontally, the strength of the soil is around this value. Okay, so choose, it's around this value. And at liquidity index of 0, so somewhere here where you are at plastic limit, the strength is over here. what people have observed is, this arrow is not very nicely drawn. So what people have observed is somewhere from here to there, the range is 100 times. In other words, it's a good number to remember or to think about. That at liquid limit, my strength reduces by 100 times the strength which would have existed at plastic limit. Okay, so it gives a good feel. So my strength, if a strength at plastic limit is say, take a number is 170 kilopascal, your strength over here would be 1.7 kilopascal. That's the number to think about. Okay, so please, this in fact, this set of curves, the first time developed by Skempton and Northey. In fact, Northey was a student of Skempton. They worked on this. It's a good number to remember. Okay. There are probably a few terms which in the next 1 or 2 slides we'll quickly go through, and if you can jot these numbers or these, at least the terms. The first one is soil sensitivity. Sensitivity means the strength which is lost due to remolding. So if there is no loss in strength, we say the soil is normal. Okay, has sensitivity of 1. So there is a range. So sensitivity would be defined as a ratio of strength. When we say strength, we refer to undrained strength. Normally, undrained strength is referred to for normally consolidated soils. We'll come to this much later. For the time being, just remember it's a strength. It's a strength of undisturbed soil to the strength of remolded soil. So it's a ratio. If this ratio is 1 to 4, we call this as normal. Fortunately, in our part of the world, unless you look at some of the soils which are are highly over consolidated, but most of the soils in our part of the world are normal, meaning their sensitivity is 1 or maybe 1.5 to 2. Compare this to the quick clays, which have sensitivity of more than 10, meaning the strength will drop by 15, by 15 if you remold it. Okay, that's called as sensitivity. The next one is called as thixotrophy. So thixotrophy, thixotrophy is a term used for when the strength is regained. So with time, if the strength regains, however, this regain should be done at constant water content. If the water content changes and the strength regains, it's something like consolidation. So we are not looking at change in water content. What we say is, if the strength regains at constant water content, it's called as thixotrophy. This regain would be partial or full. That does not matter as long as there is regain. The next one is called as relative density. It's more important for granular soils. Again, it's a ratio of maximum void ratio you measure in the laboratory, meaning void ratio you measure in the loosest state, to minus the in situ void ratio at site, divided by the difference between maximum void ratio and the minimum void ratio. Void ratio minimum would be the dense. You shake the same sand and minimize the void ratio. So there is a table which again is a handy table to remember. Please, this is important, and many a times this is quite easy to. It gives a feel. You remember the hump, stress strain hump which spoke about earlier in earlier lecture today. The size of the hump is controlled by this relative density. Okay, if it is loose, there won't be any hump. If it is very dense, the hump will be high. Of course, we spoke about the hump in terms of angularity. Angularity or interval also plays a role. Okay, it leads to the last definition, which is called as activity. Activity is defined as the ratio of plasticity index to the percent finer than 2 micron, or I can restate this that it is the ratio of plasticity index to the clay content. So if activity is more than 1.25, we call it its active clay. Usually the black cotton soils of India which have morillonite clay content are very active. Okay. So before we conclude today's class, we still have about 5 minutes. Can we have questions, please? Yeah, please, raise a hand on the left-hand side of the screen if you have a question. In the next class, we will look at clay mineralogy. Right? So we'll probably spend about 1 hour on clay mineralogy. In today's class, we have looked at particle shape and size. We have looked at Atterberg limits. We have looked at a few terms, a few definitions. If you have any question, a quick question, we can still have it. It's the same file which you have probably downloaded it last time. So again, you can download this right now again. Okay, PPT download access is given. Please right click and it is there. However, it is the same presentation as last. It is continuation of last lecture, so you would not be able to use the same PDF file. Okay.
Good morning, sir.
Good morning.
Can liquidity index of soil be negative?
Yes. If you look at the definition or the term of liquidity index, let me just go back. Let me just go back. In fact, it's not very visible on this curve, but this represents 0. If I go down, it's negative. It can be negative if this water content is less than the plastic limit. So it's negative. Remember we said water content at slightly less than shrinkage limit, your degree of saturation is still 1. So in other words, this entire set of curve is for undrained strength. Okay, we didn't touch on undrained, but undrained strength would normally be measured on saturated soil. So it has been generated from saturated soil. So even if water content is less than plastic limit, your soil is still saturated, but liquid index is less than 1. That's a good question. Any other question, please?
Sir, to finding the liquid limit in Casa Grandes, we are plotting the graph between we are taking similar graph for the Casa Grandes, that is number of blows versus water content. But in case of cone penetrometer, we are taking the coordinate in x coordinate graph, sir. Why don't we take similar graph there?
Well, it would not matter. In fact, if you look at it, the penetration, in fact, penetration is the range is within 10. So if you look at penetration, you're looking at a penetration of something like 10 millimeters, and it goes down to 30 or 40 millimeters. Whereas the number of blow count ranges from something like 10 and it goes to 70 or so. It can even 60. Some tests you can even go up to 60. It's a large range. And if you try to plot this in normal scale, you can still do that. In fact, there is no harm in doing it in normal scale, and you just curve fit it. You curve fit the data, but the error in curve fitting the data in normal scale is much larger than compared to the error which you curve fit in log scale. All the error in log scale get minimized. So the number of the points actually string along a single line. It's much convenient to plot in semi-log scale for Casagrande, but there is no harm. You can in fact go ahead and plot in normal scale as well. Okay. Any question, please? Thank you. Okay, we come to our end of our session. Okay, it was a wonderful session today. In fact, the first 3 classes I would say are more of introductory. So I'm not sure how much new or innovative things you have picked up in the first few hours. But I request you to go back home and look at the textbooks and see whether you spend about half an hour on just to review what has been covered up today. Okay. There's one last question. I guess we can take from BTKIT.
Hello, sir. Sir, if any dimension have all the association and the liquid limit. So if the liquid limit, if the soil is the region of liquid then what the effect on the shade of soil?
It was not, your question was not very clear. Can you please repeat the question?
Sir, you show the slide of the Atterberg limits. Sir, can you show
Atterberg limit. Okay, will I lose this video? Can I show the slide? Video will still be there.
Previous one.
This figure?
No, sir. Previous one. Yes, sir. Previous. No, sir. Another. So that means no.
Is this one?
No, sir.
Sorry, let me go back. I think we started from somewhere here.
Yes, sir.
Is it this one?
Sir. Yes, sir. Some sectors, sir, there is a liquid limit in the soil and in the plastic. But suppose sir, the water content is more than the liquid limit. Then sir, what is the effect on the shear strength of soil?
Yeah, I mean, look at it in a way. The void ratio is also changing. So if the void ratio changes, as long as it becomes looser and looser, so the soil becomes loose. Degree of saturation will still be 1, and your water content will still increase. It will increase up to a point wherein the soil can no longer hold the water. So in fact, Atterberg, when he came out with these liquid limit definition, his definition, to be more precise, if I must say, was not for soil mechanics. He was mainly for agriculture. So his definition was somewhere here. I mean, if you look at it, because he wanted to look at what is the holding capacity of water for a soil, a given soil. So if you go beyond this state, it still remains slurry. Probably the strength would be zero until it becomes like water, pure water. Remember, pure water has 0 shear strength. So somewhere over here, it will just behave like water.
So the means for a type of soil, the shear strength would be equal to 0. Either it will be grainy or silty or clay.
Okay, actually your question is can you put your mic slightly away from your body and say it's not very clear.
So now it is okay.
Okay, continue please.
Sir, I want to say that you told that the shear stress will be reduced to zero because the holding capacity of water of soil will be zero. So, sir, I want to say if the soil will be grainy or clay or silty or the with organic material, then for all the they will be zero, na?
Put the video. Okay, move. Put your question very slowly. Yeah, you don't mind. We were just playing around with the screen. We could not, get it. So please, can you move your question slowly? Yes, I'm looking at you. No, you ask your question. Come on, don't feel shy. Come on, take back the mic. Take back the mic.
So, sir, is the shear strength will be zero for all types of soils, na? But to clarify this.
You say shear strength is zero. Okay. Shear strength is zero.
All
And
soil. And sir, shear strength will be zero आएगा ना आपका?
yeah, shear strength will be zero.
Fine, thank you.
Okay, thank you. Time is up. I have to, close this session. Thank you.